Okay, so welcome back to the post-lunch session. I don't think I need to introduce Dr. Abhnil Prasad from UNSW Sydney. Is kindly agreed to give a tutorial on CMIP 5, CMIP 6 models and how you could play with those. Abhi, thanks a lot for doing this. I know it's already beginning to be the evening in Australia. Thanks.
No worries, Vishal. Thanks for the invitation. Yeah, it's a pleasure to host this tutorial on CMIP 6 data. What I'll do is basically for the first 15 to 20 minutes, I'll just give an overview of the CMIP 6 datasets, how we can access them and what it could be used for, what are some of its limitations. And then the rest of the time we could spend on looking at some of the notebooks that I've created. I will share the details in a few minutes. It's all hosted on a GitHub repo. So what we'll do is probably use that GitHub repo to download the notebooks, and then we can go through it, whereby I will demonstrate how we can use it to access the data set and do some simple analysis. And then there's some other challenging problems that we could look at and see how we go with that. So what I'll do is I'll share my screen. Just give me a sec on the presentation that I created. So can you see my screen?
Yes, we see your screen.
Okay, so just I think to give everyone a flavor of like where things begin. I would like to say that I borrowed some of the materials from one of our earlier workshops that happened at AOGS this year. So some of the things might be familiar to people who might have attended it, but I've added few new things. Before we go into CMIP models, it's best to start with the experimental structure and what we know about the MIPS. So in terms of short history, CMIP in 1995, the working group on the coupled modeling, WGCM established this CMIP project for coupled global models. And its main objective was to understand the past, present, and future climate changes arising from natural and anthropogenic responses to changes in radiative forcing. The idea of having CMIP was to, first of all, drive the climate modeling research, and then also help support policy development. And as you know, the most important goal of CMIP was to make this multimodal output publicly available, so that students, stakeholders, policymakers can have, can use the simulations to make useful decisions. So CMIP 6 is kind of bigger than ever. So you can see that in this figure here, you have all the way from CMIP 1 to CMIP 6. And you can see the volume of data set that has, exponentially, I think, grown over the years as the MIP generation has followed on. So, and this is the geographical map, like the countries that contribute to CMIP models. And right now, or in the last CMIP models, we have 100 models from more than 40 modeling countries. Centers across 27 countries. And I'm here in Australia, so we also contribute to the CMIP modeling simulations. We have India is also contributing as well, and then we have a lot of centers in Europe, US, and in China as well. So, and you might be already knowing this, that CMIP data sets are quite critical in supporting the IPCC assessment report. So it's basically the backbone of those reports. So most of the findings in the report are based on the CMIP-6, on the CMIP data sets. So the latest is based on the CMIP-6 simulations. So each modeling center produces, simulations, which includes hundreds of variables. So there are several variables. You have variables for the land surface. You have variables present in the atmosphere. You have ocean related variables as well. A lot of so there's like heaps and heaps of variables which are available, and these are all standardized in the CMIP framework. The timescales we work with is basically we have outputs at hourly levels to monthly timescales. You have different scenarios, so you have runs in the past, future with different emissions, and also we have simulations for the paleoclimate. So there's many ensemble members, and it already the order of magnitude of data set is around more than 14 petabytes. And this is just an example of the Australian supercomputer, which stores CMIP data. So the data is backed across several nodes around the globe. So it's all safely backed up for users. So the CMIP-6 structure is basically shown here in this diagram. There's the whole deck. You can see that you have a lot of simulations here for looking at different sort of processes. You have models that look at regional phenomena. You have like the clouds and circulation theme as well, and then you have different MIPs associated with that. You have, for example, you have the CAM MIP, which looks at chemistry and aerosols. So depending on what probably interests you the most, you could go to these sort of themes and then grab the appropriate data sets or the appropriate MIP to look at. So for example, if you're interested in regional phenomena, so you want to look at, let's say, monsoon dynamics over the Indian subcontinent at higher resolution, then you'd be looking at the high resolution MIP dataset or the codex. This is for impact. So these are regional sort of simulations from driven down by CMIP-6 models. So again, these I again mention that the MIPs are quite important because they obviously work with different response to forcings, and you have different scenarios. So you have different SSPs, different land use change, and different geoengineering sort of mechanisms that go in to build the scenarios. And then this is quite important as well. The SSP scenarios, it's known as the shared socioeconomic pathways. So these are the scenarios, the alternative storylines that the world might develop over the coming century. So what we have here is, let's say, on the top scale is the SSP scenarios going from 1 to 5, and then on the Y scale is the forcing. So you can see SSP 1 to 6 is a greener scenario looking at sustainability with lesser forcing. And then as we go to more extreme scenarios, you can see that you have the middle of the road, which is SSP 245. And then you have this fossil fuel development. So for example, if fossil fuel is continually used, then we are looking at SSP 585, which is fossil fuel development. So the simulations are run using these scenarios, and you get all the results are compiled accordingly based on the scenarios. I've already talked about that. And this basically shows what the global surface temperature change relative to 1850 and 1990 looks like under different scenarios. So you can see that, you know, the lower order scenarios is what we probably want to achieve, but you have the higher end, the fossil fuel development scenarios as well, which could give a mean surface temperature change of around 5 degrees by 2100. So before we use CMIP data, it's good to understand some of its limitations. So we should always remember it's a model, so it's not perfect. So it has its limitations. It's, you know, it's always good to know the limitations before you start using this data set. In order to understand your data, it's also important to understand what sort of assumptions are there. Based on what you're probably studying, then you would have to comply with the relevant data set that works well with your assumptions. The other thing is there are issues with parameterizations in the model as well. So it's good to understand how the model, what sort of parameterizations are used in the model. And that gives rise to limitations, because then if you understand these things, then you would understand the sort of limitations that the model will bring about in your studies. There are many different types of limitations that you should consider. So these include, so there are limitations which are process-based. So limitations that are related to processes, physical processes that are not simulated well in the model. And then next is the computational differences or limitations. So just because of the computational requirements, the model has limitations. So one could be just related to resolution, because higher resolution would require higher computational resources. Then the other thing is looking at the packages that are being used to run the simulations. We also have to look at model families. So there's many centers running models that probably relate to similar families. So they could be clustered in one, for example, in one domain. So if you want your results to be independent, then you have to look at models that are sort of interdependent as well. And then also there's limitations related to scenarios. So obviously the CMIP-6 simulations are run with the number of accepted scenarios because of limited computational power. You cannot just run all the scenarios that you wish for. So that's also a major limitation. So in terms of process-based limitations, we could divide it into processes that correspond to the atmosphere, land, and ocean. So some of the processes that are limited in CMIP models is convection, for example. So convection is the way it is parameterized can cause issues. So you have to be careful with what models and what resolutions you use, and what shallow and deep sort of schemes are being used in the models would affect your results as well, especially if you're looking at things like rainfall, extreme rainfall sort of predictions. The things like oscillations like quasi-biennial oscillation QBOs that are not represented well in some of the models, that's a well-known phenomena, and that's one of the problems in the CMIP, some of the CMIP 6 models currently. You have the issues with the double ITCZ problem, for example, it's more prominent in some models than the others. There's also limitations or uncertainties in modeling the cloud aerosol interaction. So that's also an active area of development in the modeling community. And likewise, you have for the land, you have issues with vegetation dynamics, the soil moisture and hydrological feedbacks are sometimes also not represented well in some of the models. In terms of ocean, you have the land and sea breeze dynamics that sometimes get misinterpreted in some of the models. There are a lot of papers talking about these sorts of limitations, and I'd encourage you to read some of those when you have time. The reasons behind the process-based limitations can vary, but as I said, can be related to resolution of computational limitations as well. So you can see that many processes happen on a smaller scale. So then the resolution of many CMIP6 models, so they're just not resolved properly, and that could be an issue because if you don't resolve, let's say, for example, topography well, then many processes that are driven by topography would not be modeled properly. There are also computational issues like numerics and compilers that could be different, that would give you slightly different answers. Access to supercomputers also plays a major problem because if you don't have big computers, then you won't be able to run multiple scenarios. And yeah, apart from that, the computational resources and costs as well could also affect these sort of simulations. And the other thing to consider is the input data set. So climate models read in a variety of data sets to force the model. And some of these are based on, for example, historical observations. Some are based on estimations of the future of climate. And these data sets can cause issues such as you can have uncertainties and biases in input data sets. Not all modeling centers, they rerun simulations when data sets are updated. And then obviously lack of quality of observational data sets. So they would also give issues in terms of like the simulations you get in the end. I've mentioned this bit about model family limitations. So CMIP models, as I said, are not independent. So you can see from this study from Kumar, you can see that there were 114 models in CMIP6, but only 12 main model families. So they cluster around 12 model families. So if you happen to look at let's say a problem, and if you don't subsample your models accordingly, then you might be biasing your results because it might belong to the same family of models. So you have to be careful with that. So those are some of the limitations of the model, the CMIP dataset. But still, it's useful because it gives us some information about what might happen in the future. We can compare it with the historical, and we can see the physical processes of importance, and also we can look at these natural hazards that would become more common in the future. So it's quite useful to use as well. So then comes the question about accessing this data set. So as I said before, this is big data, it's massive, but there are easier ways to access this data set. And I'm here to probably tell you about few methods that you could use to easily get access to this data. So it could be accessed in several ways. I will share with you some codes on accessing it with the ESGF API, the Google Cloud and Intake ESM. So these are some of the methods that I would show how we can use them to access the dataset. Of course, there's an errata service that is available. So it's a key resource. So it's always good to check that the data that you download is the latest version and has been fixed with. I mean, if there was an error, or it would have been fixed. So it's always good to keep track of the version of the dataset. So the ESGF website is where you have the complete collection of datasets. So if you go to this URL, you would get the complete, the website hosts all the datasets. So you'd get at least pointers to where the datasets are sitting. The advantages of using the website is that it gives you a complete collection of data. It's linked to the errata system. It's quite user-friendly, and it also gives access to direct downloads to local drives. But the problem with this is that it's quite slow in speed, so the download speed could be low, and you have limited sort of automation requirements. So you cannot automate the large scale download. So you might have to sit through most of the downloads, which could be a pain at some stage.
Uh,
But
Abhi,
then, yeah,
yeah, is it okay to ask a question in between?
yeah, sure.
Yeah, I was just wondering about this errata system. Can you say a couple of words about that?
So yeah, if for example, if we go to the ESGF website, when we look at a data set, usually you have, if there's some erroneous sort of issues in the data, then in the metadata you will have some information about what the errors would be, or what data set could be discarded. So that information is also present. So sometimes we overlook that and we just blindly use the data set. So that's not usually a good thing to do. So it's the errata system tracks all the errors in the data set. So essentially you'd know if there were errors in if there were any errors in the data. So most of the data set gets they take it down and then fix it. So but you'll have in the metadata there's some information about which, like for example, which variables were removed, or if they rerun anything, then they would let users know.
Okay, yeah, thanks.
Okay, so the other component is the ESGF API. So the API is most these days is quite commonly used for different services. And ESGF API gives direct access to the so you could use query language to get information out of the ESGF platform. So it has most complete collection of data. The important thing is that it supports automated data access because it's an API, so you can use it in your coding language to ping the database. You could do custom search queries and you can refine your results. The only disadvantage is that it requires a bit of API knowledge and programming skills, and there might be some issues related to dependency. So you have to the installation process requires some dependent packages that the API uses. The other way you can access CMIP 5 or 6 dataset is the cloud services. So, for example, Google Cloud now hosts a lot of CMIP 6 dataset. There's also some data hosted on the Amazon Cloud service, also probably on Microsoft Azure service. So the advantages of having data on the cloud again is it's because it just makes things much easier. You can get very high download speeds. You could in principle run you can do analysis on the cloud as well. So it really goes well with scalable data analysis and big data analysis on the cloud. The disadvantages of it would be that sometimes it would require, let's say, access to Google services. You might have to pay for some of these services, especially the computes. Most of the data set is like freely available, but you might have to pay for the compute, and also you have to be familiar with, let's say, if you're using the Google Cloud, then you have to be familiar with the Google Cloud services. Another method is using intake ESM. This is also quite easy to use because it seamlessly integrates with Python. It has an easier metadata management and querying system. So it's somewhat related to the ESGF API, but it's just we have another, let's say, Ben. It's some sort of a wrapper around the API, so making it much easier to query the data set. So all the data sets are pre-built into a table, and you just query it through the intake ECM to get the metadata out, and then also get the you can also read in the data quite easily. The only problem with that is that it requires some additional configurations and setups, and it also because it comes with a Python package, so it has some dependency issues as well. So you have to be careful while installing it. So those were some of the methods in which you could access CMIP data. And then obviously there are a lot of data analysis and evaluation tools that can be used for analyzing CMIP6 data. And these are some of the tools that are available. You have Python, which is a programming language, widely used programming language, which could be used to analyze CMIP dataset. You can also use R if you're familiar with R. It also comes with a lot of statistical packages, and you could, in principle, use R to also analyze CMIP datasets. You have Julia, which is also an emerging programming language, which can also be used for analysis of CMIP6 dataset. You have platforms like ESGF, which gives access to access to resources for analyzing CMIP datasets. And this also includes the Pangeo framework. So Pangeo framework is where they pre-build scalable sort of compute for using CMIP datasets. And these are some of the widely used resources for using and analyzing CMIP data. So in today's tutorial, I'd be just focusing on Python, but obviously, if you go to this URL, you can find some examples of using how you can use the other resources. Apart from the coding language, there's some very nice packages. So for example, in Python, you have like packages like xarray or xcdet, iris, pandas. These are some good packages that would assist in analyzing the CMIP6 dataset. So I'm sure if you're using Python, then you might have at some stage used some of these packages. There are some analysis tools as well. For example, Panoply from NASA, which gives you access. So it just gives you access to read data sets of servers. You can just quickly plot things. You have the NASA Giovanni tool as well, which gives you access to data sets, especially some observations data sets. So if you're doing some evaluations, you could use that. There's KNMI Climate Explorer as well from Copernicus, which gives you access to using some of the CMIP datasets. I won't go into much detail about benchmarking tools, but there are tools like ECM-Well tool, which comes with recipes which you could use for benchmarking and validating CMIP models. And of course, there's this because some of the data sets could be downloaded in netcdf formats. So you have these common command line operators in which could manipulate netcdf files or view files like ncview, nco, and cdo, which could help with manipulation of some of the files that you download from the CMIP database. And another interesting toolkit that's available now is the IPCC Atlas. So this is where you can go in and visualize the IPCC regions, and you can look at interesting patterns from different CMIP6 models. So as I said before, today I'll just look at Python and how we could use the Python programming language to access and utilize some of the CMIP6 dataset. That brings me to the end of the slide. So if you have any questions related to the slide, we can probably spend some time on that before we go to the...
Are there any questions? Yeah, maybe. So CMIP models are on different resolutions. So what are the, I would say, what care do we have to take before we really look into the data?
So yeah, that's an interesting question, Vishal, because as I said before, it really depends on our research question. So what we are looking at. So for example, if you're looking at something which is related to impact, on the society, so that would mean going down to the highest resolution that we can get, and that is where the high resolution MIPS come into play. So these are global coupled simulations run at higher resolution, so of the order of like 50 kilometer to 25 kilometers at some instances, and they also have high temporal information as well. But then if you're interested in a particular phenomena, let's say just if you want to look at just impact of clouds, then you have to go to the MIPS that are concerned with looking at cloud feedback. So you have MIPS associated with that. So you could go and look at that, and that would mean that there might be simulations that could be run at even different resolutions from different centers. So it really depends on the research question, I guess. And then accordingly, you have to choose the right simulations. Now, one thing with CMIP models is that we do have the codex simulations as well. So these are regional simulations. So there's some downscaling done. So for example, if someone is interested in looking at extreme rainfall over India, then they would look at the relevant codex dataset for India, which would be much higher resolution and would likely resolve some of these, subgrid level dynamics that you don't get in resolutions of the order of 100 kilometers. But if you're interested in looking at, for example, cyclones, which are large scale, then you would probably go with these COSA resolution simulations because that they would at least resolve massive systems like cyclones, and that could be done as well. So it really depends on the research question.
I'll ask another question. As from students' point of view, so some of these models have, say, 50-kilometer resolution, but what is their effective resolution? At what scale can we think there is a kind of strong signal to noise ratio? I agree that that would change from phenomena to phenomena, but if there is any rule of thumb.
I would say that anything of the order of desirable would be of the order of 50 kilometers or so. But if we have something like of the order of 25 or 10 kilometers, then it's more reasonable. Especially if you're thinking in terms of like cloud resolving models, for example, then the scale would be of the order of less than, let's say, 20 kilometers or so. But obviously, we don't have many simulations which are in that range, global simulations. I think the global runs are quite coarse because it's a coupled model, so we have to consider oceans as well, and that brings its own challenges, especially with the feedbacks that you get from the land and ocean.
Sure. Yeah. Thanks. Because I think some of the students here might at some point want to ask a particular question on CMIP, and they might have to be aware about the suitability of CMIP in answering that particular question. For example, quite a lot of times, especially those who come from outside the climate science community, they want some understanding of impacts at a grid scale. Say something like on Mumbai. Mumbai is within, say, within one grid box. And practically one has to give some information. So from that point of view, if you have any comments, that would be nice.
Yeah, I think that's something that is always, I think, bothering modelers. So for making decisions at ground level would require obviously high resolution data set. And currently CMIP models just provide us with this background information if you're looking at that scale. So obviously we might have to downscale, use the CMIP6 data set as the boundary conditions and downscale it to that level. And that is where other models would come in, and CMIP6 data set just becomes the driving data set. We could, in principle, use the high resolution MIP data set to give us, let's say, a first approximation. But if you want detailed spatial, temporal sort of dynamics to be resolved, then that is where we could always use the CMIP6 dataset as boundary condition dataset, and then we can downscale it to the resolution that interests the local regions or the phenomena that needs to be resolved. There also, as I said before, there's the codex framework, which sets the scene for the regional simulation. So there's already downscaling done to certain resolutions. So I think it might be going to 10 kilometer or 4 kilometers in some regional codex simulations. So obviously, one can use that data set as well if and these are already downscaled if you don't want to do any downscaling yourself.
Yeah, thanks, Abhi. Are there any other questions from students? I've been trying to pretend like a student, but are there any real student questions? Okay, I think we can move on then, Abhi.
Yeah. So what I'm sharing now is my GitHub page. I will share the link. I don't know how easy it is for everyone to see, but I don't know where's the chat gone. So I'll share my screen again. So what we plan to do next is pretty much look at the notebooks that I've created on the GitHub page. So if you go to https github.com/abhnil/md_workshop, then you get this. You get to the repo where I've kept the notebooks. So I'll just go slow. So there are two ways to run the notebooks that I've created. One is you could directly click on the binder link, and it will build the code on a cloud service, and you could just run it off the binder service. The other is you could clone the repository on your local machine. And to do that, I've already given instructions here, what you need to do. First of all, you'll need to clone the repository on your local machine. You'll have to cd into this directory. Then you'll create a virtual environment, a virtual Python environment, which I've called here CMIP6 environment. And then after you create that environment, you'll activate that environment using this command here, source CMIP6 environment /bin/activate. And then once the environment is activated, we'll install the packages that are required, and it's already present in the requirement file here. And then we can start using the notebook. So what I'll do is I'll probably do it on my end so that you could see what I'm doing.
Abhi, there's one request to enhance the font.
The font, okay. I can go bigger. Is that better?
I think so.
It can. can everyone go to this GitHub page? It's it's a public repo, so you should be able to see what's in this repository. I can go bigger if you want. So one thing you could do is just click onto this. If you can go to this web page. If you're not very familiar with creating Python environments, then you could just click onto this binder link and it will build a Docker file, and then you would get something like this, which is a Jupyter environment. If not, then what we could do is we could just open a terminal and so we might have to just use this code, copy this, and then paste it on your local machine. So I'm just cloning it on desktop here, and then you can see I can get into this directory. Is everyone following me? Is people familiar with Python, or do they need some more help?
Yeah, yeah, we are able to clone the GitHub page.
Okay,
Yeah.
so you've cloned the GitHub page. Then were you able to create Python environment? So it's just copying that code, right? And then I'm just inside my working directory, and you can see once I do that, I create CMIP6 environment in that directory. So it's just copying those commands, and then I try to activate. So source CMIP6 environment /bin/activate would activate that environment. So now you can see I'm just having this, the CMIP6 environment is loaded, and that's what I want. And then we can install the requirements file in that environment. So after we activate that CMIP6 environment, we can then install the requirements.txt file, which is already in this repository. So and that just to be on the safe side, it's good to upgrade pip, which is our package installer. So so now, because my CMIP6 environment is activated, I can I can just go here, copy that, and I can just upgrade pip. So you can see it updates pip, and then I can just copy the requirements file, do the same thing. So pip install -r requirements, basically what it does is it goes in and looks at this requirements text file, which is all the packages. So you can see I'm installing Cartopy, intake ESM, GC SFS. This is the utility to be used on the cloud service. I'm also using Boto3 for the AWS. There's a Azure storage blob as well. And then you have the ESGF Python client. You have Siphon, which helps with looking at URLs. You have the Jupyter Lab package, which basically is an IDE for us to run the notebooks. We have I'm also installing X-ray, which is useful for reading NetCDF dataset. And then S3FS is a client which works with the cloud services as well. And I'm also installing DASC. So DASC is for distributed computing if you want to run things in parallel. So once you do that, once you run pip install with that requirements file, what it will do is it will go and start building your environment. So it will start installing all your packages on the environment that you have created. So this takes a bit of time. The other thing, as I said before, is you could also click on this launch binder if you don't want to install it on your machine. What it will do is it will start building a Docker file on a cloud service. And it essentially does the same thing. If you see the log files there, it starts to build the cloud service, and you would get the environment running in a few minutes. So you essentially have the environment already installed. So that's quite quick as well. So either you can do that, or you could, as I said, you could do it this way where you want to install it on the local machine, on your local machine. So I'll just pause for another 5 minutes while you try either of these methods to set the environment up. And if anyone is having issues, can probably ask me, and probably I can try helping from here. Otherwise, there may be some good Python users out there who might probably try help each other to get this going. So you can see now, for me, it has already installed the environment, and already in you can see if I cd into the CMIP 6 environment, it has all the installations are already in the libs directory. So
I was wondering, maybe shall we request a raise of hands for how many are using binder versus local installation? So binder, how many? And local installations? I mean the rest, but oh, I see. Oh, mine went through on the yeah. So
is anyone still not set up?
actually, there is one error. Adrian Tompkins is getting on his Mac. Maybe I'll hand it over to him.
I was just wondering if everybody got the same error as me. I tried to install Wheel as well. I get mine bombs on the build saying getting requirements to build Wheel did not run successfully when it's just on the number package. So look. Let me see if I can find it. I'm going to Google it. Did anybody else in the room get the same error? Or did it build okay for you?
Is it like, may I ask which version of Python you are running?
3.13.0 from October the 7th of this year.
Okay. I think it should, because it's a newer version, it shouldn't have problems.
Yeah.
But if you want, you could probably try with an older version, a bit older one.
Yes, it's it's a version actually. Runtime error. I find looking further up, it says cannot install on Python version 3.13.
Yeah.
Versions between 3.9 and less than 3.13 are supported.
Yeah.
Okay.
So I think most of these packages are quite old, so maybe that's why it might not be supporting the newer one. Maybe we're still fixing bugs for that.
Yeah.
So probably just install it with an older version of Python, and that should work.
Requested a raise of hands, and it seems around 80% of people are using binder, 20% using local installation.
Okay. So for those that are using binder, it's straightforward. You have the notebooks. If you just click onto the notebooks, I would like to start with the get CMIP 6 data notebook. So maybe just click onto that. Those who are on your local machines, oops. Okay, maybe I close that. So to run the notebooks on your local machine, you just have to CD into the notebooks and then execute the command because you want to run it with Jupyter Lab. We've installed Jupyter Lab. So you just say Jupyter Lab and the name of the notebook, which is get CMIP 6 dataset. So you can see all the notebooks are there. Just CD into the notebook and then say Jupyter, sorry. You can just call by the name of the file, or you can just say Jupyter Lab, and then it should open up a browser, and you would get the notebooks as well. So either way, you could open up the notebooks. I'm just probably use the binder here. So if everyone is happy, then we can start, or maybe just wait for Adrian to fix his environment.
You can go ahead. Don't worry.
Okay.
Just trying to work out
Yeah,
how to kind of retrograde my Python.
that's fine. Okay. So this is now. So I'm sure everybody, if you're not familiar with notebooks, this is just the simplest IDE that you could use. It runs in the browser, and so what you could see here is that the codes are written in Markdown. So I've created a Markdown. It's Markdown syntax. If you want to write something, then you use Markdown. So if you run it, then it just synthesizes as a text, so renders as a text. So what I'm shown here is, yeah, I just use this from AOGS. And I've already mentioned about the pros and cons of each method. So the first thing that we want to do is access CMIP data using the Google Cloud. So to do that, the very first thing is we need to import all the relevant modules. So here I'm importing pandas. So importing pandas SPD. So this is where you can render your information in tables. I'm importing Xarray. So this is to read the netcdf file. I'm also importing ZAR. So ZAR is a format which is similar to netcdf, but it's more consolidated. So it's used in the cloud service because it's already you can read subsections of the file and not the whole file. So it becomes very efficient in terms of if you're reading dataset of cloud. There's a package known as FSSpec, which is used for mounting drives on the Google Cloud Service. I'm importing matplotlib, SPLT. This is a plotting utility, and also Cartopy. So these are all these last two are the plotting utilities which we would use later on. So I would execute that. To execute, you just have to push the play button, and you can see once it completes, you would get a number in front. So that means that line has successfully executed. So next, what we do is, because we are on the Google Cloud, we want to explore the data catalog. So we want to see what sort of data set is out there. So that is when I run this second cell, which says that I want to read the catalog. And this is where the catalog is. This is the link to the catalog for all the files that is available on Google. And once you run that, it will just go and read this URL that's provided. So it takes a bit of time, but essentially it will spit out the catalog after it has gone through. So you can see here, I have read, and I'm just spitting out few lines of the catalog. If you want to look at the full catalog, then probably you just have to print TF, and then you see this whole list of, it goes, you have 5, 2, 3, 7, 7, 4 rows. So that's the number of different simulations that's available. But right now, if I just said df dot head, then it just gives me just a small flavor of what the catalog would look like. So essentially, the catalog is quite big. So you have a lot of data set on the Google Cloud. So next is we need to look at the columns of the data frame that relates to the CMIP6 control vocabulary. So if you click onto this, it will take you to another web page where you could see how CMIP6 dataset is kind of described. So you can see that you have the file names, how they created for CMIP6 and CMIP5. So for CMIP6, you start with the MIP era, then you have the activity ID, then you have the institution ID, which institution the model is being run through, the source ID, the experiment ID, what sort of member, the member ID, the table ID, the variable ID, the grid, the version, and then you have the file name. So, and then if you really want to look at the complete list of CMIP variables, this is also available in a table. So you can see all the list of variables that are available. So you can filter through them. You can see what, for example, here you have, see the name, the field name, what the long name is. So you can just broaden this a bit, and then what's the standard name, what the unit is. So you can sort them, you can by variable. So you can essentially look for a variable that you want, and then you would know which what it is called in the CMIP6 standard family of names, what its unit, and then accordingly you could download that data set. So using these two sets of information, I can query the database now because I know what's in the catalog. So what I've said that the activity ID is obviously I want CMIP. CMIP, the table ID is a mon. You want the variable as surface temperature here, so that's DAS. And I'm looking for the historical simulations. And once you do that, let's just execute it. You can see that for this query, I get a lot of responses again. So you like 635 data sets that show up because I didn't filter it by institution ID or source ID. So all the data set is kind of retained. If I do want to filter it with institution ID or the source ID, I can always add it to the query here in a similar fashion, and it would filter the data a bit more. So is everyone following up till there? Because you just have to click onto the play button and it would execute.
Yes, yes.
Um,
We are able to reach, yeah, do that. Like we reach there.
okay. So next is like now let's say I want to filter the data. So from here I've got all the surface temperature values for historical, but for different institutions. I want to filter it for those that are run by CSIRO. So this is in Australia. So I can go to this DFTS that already we created, and I can build the query again, querying for CSIRO institution. And once I run that, then I get more filtered data sets. So you can see now all the institutions are for CSIRO. And this is, again, all this is done using the query that is being generated from the catalog. Now you could try, for example, you could try sorting it for some other institution. So you can, let's say you can probably try doing it for IPSL and see what sort of data set you get. So you could, in principle, go and change this for whatever institutions that you want to filter the data for. Or you could filter it for, you could go up here and change the scenario to SSP 585. So that's all customizable. And accordingly, you can filter the data set based on those sorts of queries. Was there a question?
It's working fine.
Yeah, another thing I should mention is that if you look here at the data set, because we are on the Google Cloud, you can see it gives us the location of the where it's on which bucket the data set is. So that's on the ZStore database. And you also have the version information, you have the member ID, you have the experiment ID. Because we've already filtered, if you go up, as I said, you can customize this and look for other options as well, based on, oops, where did I go? These are the variables part. Yeah, based on these sorts of information, you could. So, for example, I didn't mention this. The experiment IDs are all listed here as well. So you can see you have PI control, you have the CO2 experiments, you have the AMIP experiments, you have the historical, so AMIP historical, the projections as well. And then yeah, the other information is about how the table ID is listed. So you can see that you have, I'm using a month because I'm looking at monthly atmospheric data set. So for example, here, this is looking at monthly data set. So if you want, let's say, if you want to find or filter for daily, then you have to use this CF day as your table ID. And then accordingly, you'll filter the data set. So all this so you can see there's like so many ways to filter the data set. It's just knowing which ID you have to use for table ID. And then accordingly, you have member ID, you have the grid IDs, and the list of experiments. So all this is already listed here in this document, which I mean I've already provided the link to. So you can play with the different IDs and see what sort of data set you filter. So once, let's say, if I just continue, I would say that after I filter for CSIRO, I can then load the data set. So what we are doing is basically, you can see I'm loading it from the ZStore values, because that's where the data set is sitting on the cloud. So if I run that, you can see this is the link where this data set is. You can see this is for CSIRO, historical monthly surface temperature values in the historical simulation. Once I have that link, then what I can do is I can create a mapping interface. I can mount the data set onto my local drive in a nutshell. That is what we are doing. And to do that, what we are doing is we're using this FSS spec. So this is the package which helps to mount the data set. And it has special functions like get mapper. So it just maps this data set onto your local Jupyter drive. And then because it's a ZAR format file, as I said before, the data set that are stored on a cloud service are not usually netcdfs, but they are ZAR files. So you have to open using the ZAR toolbox. So that's why you're still using X-ray, but we're not opening netcdf, but we're opening ZAR using this mapper function. And once you do that, what happens is it will try to read in the data set. So it takes a bit of time. You might find that this is a bit slower on the binder framework, but if you're on a local machine, on your local machine, then it would be a bit faster. So that's the beauty. If you're running it on your local machine or on your, let's say, on your supercomputer, then with good bandwidth, then it becomes much faster. So you can see when I load this data set, it is an X-ray data set with 144 latitude bands, 192 grid points in the longitude, and time dimension of 1980. And then this is the variable. You can see it's the surface temperature. The only thing is that now this data set is it's a DASC data frame, so it's in chunks. So you can see it's having it has 3 chunks. So each chunk is of the size of 70 megabits, and the total size is 208. So it just helps. What this does is that the ZAR files are always chunked, because then it becomes easier to read subsections of the data set. And this becomes quite important once you start analyzing big data. So let's say if you start reading all the ensemble members and then start doing analysis, then this data set would become really, really big. So that's when this chunking really helps to do the analysis, because it won't really fill your RAM, and your code will not be stuck, because your computation would be distributed across chunks. So because this is similar, this is an X-ray. I'm assuming that many of you know what X-ray is and how you can use it. But if you're not familiar with X-rays, there's a nice tutorial. Let's see. Yeah, so if you go to X-ray documentation, they have nice tutorials and videos on how you can read, X-ray dataset, how you can read netcdf files. X-ray package can read pretty much netcdf, HDF, grep files, even ZAR files, as long as you install all the dependencies with it. It can read all these files. You can even visualize things very easily. You can slice and dice the data set quite easily as well. And it goes really well with the with parallel computing as well. So I think I'm probably running a bit late, so I should just go on. I'm assuming that this is like people are familiar with X-ray a bit. So once you have read the data set into memory, it's already here, then we can just easily plot. So this is the beauty of X-rays. You can use this iCell tool, and you can select So I select means index select. So you can select the very first time index. So time 0. Where is time here? So that is time. So we are reading the first one here, this time. And I can just say dt dot tas I select for the time, and then I will call that wrapper function for plot dot plot, and it will read that data set and would just give us a simple plot for that time. So you can see here the time is 18:50:01:16 at 1200 hours. It gives a very simple sort of contour plot for that time. Now I can do it for any time. Let's say if I want the 10th index, I will just say I want the 10th index, and it will look for the 10th index and plot you the surface temperature. Yeah. So this is now for the 10th index. You could also, there's several ways of slicing and dicing of X-rays, but this is one of the simplest ways for the time, just to look at the index for time. So you can see this is near surface air temperature now. But we can make this plot much nicer using the Cartopy toolkit, and this is how it will look. It's very simple to use. I've already imported Cartopy in the very first cell that I executed. So what I do is I just create a subplot with the projection as Robinson. I still say that I want the 0th time index for that variable. I put in some other information for the orientation and the color bar, and I can execute this cell again, and it will plot the same figure here in Cartopy. Yeah. So sometimes it downloads some ancillary data set when you run Cartopy for the first time. So you can see I've got a nice figure showing the near air surface temperature for that time period. You can do much more here. You can do a mean over time and then do a plot as well. So let's see if you can do a time mean. Well, that's plotting. We can still continue with the other option. The other option is using the ESGF side, which if you click onto this link, you would go to the site, and this is where you could select the data sets as well and download things directly. So you can see here, if you want to download, let's say you can do the same thing, but this is a graphical user interface. If you want to sit through this and select all these, resolutions, labels, all the information, you can select all these, instances to filter the data set, and then you can easily click on one of those, and then you can get a wget script, or you can just download it directly onto your machine. So this is also another way. It's a very easy way of getting data sets. The only thing is, like, rather than creating a query, you are putting the query yourself in these drop down boxes, and then you're filtering the data set using this URL or this web page. So this is another way of getting the same thing, but I think this becomes more tedious, because if you're downloading multiple data sets, then you don't want to sit through this and go through each individual sort of data file to download the data set. So yeah, so this is, you can see it is executed now. I've created a mean, but sorry, I didn't update the title, but this is the mean of the whole data set plotted on the map.
Hi,
So
Abhnil. Hi.
yeah.
This ESGF page is not loading for us.
Not loading.
That
Uh,
we click on that link, ESGF MedGrid search page, then it.
Okay, for me it's loading. I don't know why. Maybe you don't have good internet connection. Probably is it that, or is it? It could be. Yeah, sometimes it. I know that sometimes it doesn't work. Like I was trying it yesterday and it wasn't working, and somehow it's working today for me. There. I will maybe share this. If you go to esgf.github.io/nodes.html, then you can look at different nodes as well. So maybe if one node is not working, then you can go to the other node. So there is, as I've told before, that it's distributed all over the globe. Dataset is distributed across these centers. So you could always go to some other node, and it might one of the nodes would probably work. So this is, for example, in Germany. And yeah, this is also looks like it's working. But yeah, if you try any of these, at least one of those should work. Sometimes the data centers they're carrying maintenance and doing things, then it might be offline for a few days. But generally, it works well. The links. Okay. So the other thing is, like, if this is going through the ESGF website, but we could in principle use their API as well. So this is now the ESGF API is you click on the link, then you get some information about the Grid Federation and the API. But I've already installed the API. So in the requirements file, we've already installed the API. So if you want to use the API, you just have to use this package PyESGF. If I run that, you can see it has already initialized the API. And here, I think I've already shown all the nodes that you could query. So all these modeling centers are there, and they have all of their data set is hosted on the nodes that are pretty much here. So we can query all these nodes using the API as well. So for example, here you can see I'm connecting to the esgf.ceda a node in the UK. So I'm querying into this node here. And then if you just use the link, it basically connects to the node. So it's basically pinging to this website through an API. And then I do the same thing. Rather than choosing all the experiments and projects and all the IDs by myself, as in like clicking through this, I can build the query here using this connection.new context. So this is the query. So I'm using the project experiment ID as the facet. The project is CMIP 6. I want the monthly data set. I'm using the institution IDs, pretty much similar to what I used it for the Google Cloud. And then I can build that connection. It builds this query. And then what we can do is, like, we can take this and then we can search through this query using the ctx.search command. And then it will retain us some results. And what I'm doing is I'm just looking at the result to see what the URLs they are returning. If I run that, you will see that it will return the appropriate URL, which is It's basically an open depth URL in using the thread server. So you can see it has returned the HTTP address where this data set is sitting. And then because it's open depth service, you could just query into this link using X-ray dataset option. So you can open this link using X-rays, and that is using the open dataset function. You just have to put in the URL, and I'm just chunking it. I'm providing, I want the dataset in 480 chunks. You can obviously remove it, but it's just for demonstration purposes. It just helps us to get the dataset much easily. So you can see now once I run that, it can just go and open this dataset. And this is all on the cloud. You're not downloading anything on your machine. What you get here is basically, you can see I was interested in the temperature, surface temperature. And you can see that because I requested for 480 chunks, so you can see my time dimension is of the order 480. So it's chunked by 480 time steps. So, and then what you're getting is basically 5 chunks. So I've chunked my data into 5 different pieces, and then I can easily analyze it later on. And then I can do the same thing as I did before. We can plot the first time index in X-ray, and you can do the same thing with Cartopy. So you can see now I've shown you at least 3 different ways of accessing the same data set. So one was using Google Cloud, one was using the ESGF website, one is ESGF API, so same but using the API where you build your own query. And then the other thing you can do is using, you can access it using the intake ESM. So this is another method which you could use to extract CMIP6 dataset. So to do that, you just have to import the intake package, and that's what we do here. So if you click onto this link, it tells you about the intake ESM, what it is, how you install it. We've already installed it, how you build a catalog. So all sorts of information about all the commands that you could use for the ESM data store is available here. Examples are here as well. So if you use that link, you'll get more information about it. I think you have the collection package is also here about how you search the threads database, what sort of other packages goes with it. So if you want to learn more about it, it's available in the GitHub repository. In a nutshell, it's very similar to what we have done with the Google Cloud. They also have a catalog, but it's in a JSON format. So they've already built a table and stored it on one of their servers. You can use the URL to get the CMIP6 dataset from their server. So I'm just calling that URL, and I'm just using the intake.open ESM data store to read that URL to see what sort of dataset is available from the intake ESM package.
Abhi, so
Yeah.
what is the advantage of intake ESM over the previous method directly through Google API? Is one of them faster than the other?
Yeah, so I think the intake ESM probably has more complete data set than the Google, because Google is obviously it's a more like a run by a company, so they don't regularly update their data set. So the catalogs probably are not that much updated as intake ESM, because the intake ESM is run by the Pangeo community, so they regularly update the catalogs. So you get more complete sort of data sets probably with the intake ESM package, but it's fairly very similar in the way you access, because the catalogs might have just have some missing data sets. So maybe in Google Google's catalog, you might not have, let's say, for example, the high resolution MIP dataset, but here you might have the high resolution MIP. So that's the only difference. The other thing is like, obviously, intake ESM is now is managed by Pangeo community. So they are using probably a different cloud service. So Google is a premier cloud service. So their download speeds would differ, the bandwidth would differ. So you'll have gains in that respect, that maybe you will get much if you especially running big data, then the Google Cloud would be a better place, because that is where you can spin up machines that could run bigger clusters, and you could use the dataset. You can mount the dataset directly, whereas here you would have to request resources via the Pangeo framework.
And in terms of
But I think I have listed all the pros and cons maybe somewhere here for each of the methods. Yeah. So if anyone wants to have a look at compare what.
Yeah, thanks. Let's say somebody is working on a laptop and doesn't have to go through binder, but have his or her own installation and install intake ESM package. Then probably, of course, Google API is a private one, but maybe seamless, although at the cost of being less updated. Is that the kind of short
Yeah.
summary?
Yeah, it gets updated, but it's not on regular intervals. Maybe they'll update it every 3 months or 6 months. Who knows? But yeah, so those are some of the downfalls of using things on a private service. But the ESG API is where you'll get the complete data set, because it's pinging to the ESG website. So I would recommend using the ESG API, but for user friendliness, I think intake ESM and Google Cloud are much easier to use. The query is much easier to build because they have pre-built all the catalogs.
Right.
Yeah.
And let's say, I'm kind of in an awe that CMIP 5 was what, 1 point something petabytes, and CMIP 6 is 14 petabyte. So in general, do you think to do any, say, practical analysis on CMIP data, one would have to have either a big storage, at least so that one could download some data and process, or buy some cloud processing credits? Which one do you recommend out of these two?
So I think the beauty of using the APIs is that you can pre-process most of the data set before you even read it into memory. So let's say if you want data set only over, let's say, a region in India. So you don't have to probably read all the data set, because with Xarray, you can use the pre-process function to only retrieve the data set which is covering the Indian subcontinent. So you only download the data, and that's the beauty of ZAR as well. So as I said, ZAR formats are already the data set is already chunked. So you don't have to read all the data set at once. So all the pre-processing is available in these sorts of scripts. You can pre-process the data set and you can reduce your data size in one way. The other thing is for processing the data set. It doesn't, like, let's say if your data set size is, let's say, 100 gigabytes. Now the beauty of Dask that I was showing before here is that you could, in principle, analyze the whole 100 gigabytes of data set in a laptop which has a 16 gigabyte of memory, because you can chunk the data set, let's say, in 10 gigabytes, and you could process your data sets in 10 gigabytes of chunks, and it will just take you a little bit more time. But with parallel processing and chunking, you could analyze the whole 100 gigabytes of data set in a laptop having, let's say, 16 gigabyte of memory. So there are ways to go about analyzing CMIP6 dataset. Of course, they're like, if you have resources to run it on a cloud service with a bigger cluster, then it becomes much easier. Then you don't have to use these sorts of chunking and other options. But nowadays, with the packages like X-ray and DAS, all the chunking is done in the background. So you don't really have to do hard code it. It's already coded into DAS. So if you read it in X-ray, it will automatically read your data in chunks, and it will try to fit your available memory. It just would take more time, I guess, to process the data set, but it won't fail at least.
Right. Yeah. Thanks. So technically, one could, if one is willing to wait a bit longer, one should be able to access quite a lot of data and still process it with whatever free credits we have.
You could also do it on your local machine as well. Depending, like these days, laptops, as I say, come with 8 GB, 16 GB, 32 GB of memory. You could, in principle, run your analysis on your local machine with chunking and using Dask. It just means waiting a little longer. It is like you lose on time, but I think only thing when you scale it on a cloud cluster, then you save time because you can run it in parallel using multiple cores, and you have more access to memory. So you could just quickly run the analysis, which would take a little bit more time in your local machine because you can't scale it. You don't have the hardware to scale it up.
Yeah, thanks.
Okay, let us. How much time do I have got, sir?
Around 15 minutes.
Okay, so I think I should just rush through this. So you can see intake ESM pings the Pangeo cloud. It will obviously fail a few times, give you some error messages that got timed out, but eventually you will get the data set after a few minutes. And then the process is the same as I said before. You will read the data set okay, what did you say? You would read the data set and you would in principle plot it the same way. No, maybe I didn't run this. What did I run? I ran that one. I ran that. Yeah, if you run this, it should run through and produce the same kind of plot. Now, I think in the last 15 minutes, I gave some problems yesterday, but we won't have probably time to go all over it. But this is an interesting one that you could look at. This is creating the famous climate stripes from the one that Ed Hawkins shows in most of his talks. The task was to read the dataset from the ESGF API or using any of the methods, and the idea was, can we come up with the climate stripes? And that's what I would just quickly show. I'm sure some of you might have attempted this, but the way that I did it is just reading, again using, I use the ESGF API here, connected to the node, build the database. Here again, I'm using the CSIRO dataset, and then looking at the surface temperature, because climate stripes basically looks at changes in temperature over a period of either in the historical period or in the future projections. I build the query. I try to download the data set. So you can see I can build the URL quite easily. And then because it's open depth threads data set, I could easily read it using X-ray. I run that. It will try to read the data set. You can see it's an X-ray data set. It's having it's chunk data set because I asked it to be chunked in time. And then Because I'm creating global means, so I have to area weight it by latitude. So I create a function here, which is global mean. Sorry, was there a question somewhere?
I don't think so.
Oh, okay. Maybe I had some noise. So yeah. So I this what this function basically does is just weights area weights your the mean that I'm calculating. So to calculate the mean, I'm just area weighting it with the cosine of latitude. So that's the function. Once I build the function, I can apply the function on the data set. So what you can see here is that I'm applying this function global mean to the pre-selected data set. So I pretty much I'm slicing the data set from 1981 to 2010, and then I'm grouping it using I'm looking at yearly means. And once I run that, it will create calculate this global mean of surface temperature from 1981 to 2010 for this data set. And yes, I do the plot, so you can see how the mean surface temperature is changing, and this is for the model here for CSIRO XSCM2 model. And then, so the idea is now, how do we translate this to climate stripes? And which is fairly easy, because what we're trying to do is just create a 2D vector here, whereby we have what I've created is, you can see here, I've got the temperature from this variable. I call it DTN. I create another variable in X dimension, which resonates with the length in temperature. So you can see I create arrays for temperature in the x-axis. In the y-axis, I just use binaries, so 0 and 1s, because I want to stack the data set in a way so that I can create color bars for every length of temperature that we have in terms of years. So you can see I can do a V-stack, and that creates this matrix for temperature. And then once I get this matrix, I can easily plot it in using P color mesh. So when I use P color mesh, I can use the X on the X-axis. I just have the index for the temperature, and then on the Y-axis, I have pretty much 0 and 1s looking at, and then the color bar resonates with the you can see the values of temperature. So the interesting bit here is that we are allocating the values for temperature with the colors, and I'm using the blue, white, red color map here, so that I can translate this time series into stripes. So you can see basically these areas are much lower in temperature, so they are more blue, and then those that are much higher are more red. So yeah, so this is just showing that you can create climate stripes for any model, for any projection as well. For example, I can change the experiment ID here to SSP 585, and I can create the climate stripe for that period. So there's much more we could do. I mean, we could go more complicated. There are a lot of examples. I think I did open it somewhere here on the, where is it? Here. So if you go to this Pangeo gallery, there's like a lot of examples which you could work with. And you can also launch it in Binder. So you can run these examples on Binder. So one of the examples that I think I did ask for you to try was somewhere, I think it's this one here, to come up with the change in frequency for the zonal mean rain frequency. And I might not run it, but you could run it, but I could probably just go through the code you could see it's pretty straightforward. They're also using, the Google Cloud service to get the data set. This is 3-hourly data set, so they filter the data set for 3-hourly, and the variable ID is precipitation. So they can see it gives them a lot of data set. Because you want to calculate the change, so you have to download the historical and SSP 585 dataset so that you can calculate the difference using the two. So they grab all the models dataset. They load all this dataset into a nice data array, and then the idea was you have to calculate this sort of precipitation histogram. So you define a function, basically. That's what is defined here, based on so you create histograms for the precipitation, which is also averaged zonally. So that's why you can see this is what it calculates the precipitation histogram for a single model using the bins. The bins here is already they predefined the bins. So I've not gone into the details, but it's just binning the data set. And then once you have this function working, you could, in principle, load the data set, apply this function, and then what it would do is it will create all the bin information, all the bin precipitation data set for each model would be stored in the histogram. And then once you have that histogram ready, you could just subtract the two different histograms for the one with the one run in the future projection scenario with one in the historical, and you can create that difference, and then you can easily plot it. So you can see these are for individual models, how the distribution looks like when you look at rainfall frequency it's basically change in the zonal mean rain frequency from the future simulations compared to the historical, and this is for all the models. So yeah, we didn't have time to run through this, but if you want to have a look at it, you can do that later. There's several other examples here as well, which you could look at in your free time, and run through some of those. Yeah, I think you'll at least you've got a flavor of how you can access the data set and what you can probably do with it in terms of research. So it can be really useful once you start analyzing massive data sets. So yeah, I think that's pretty much what I've got for you today. So I'm happy to take some questions if anyone is interested in learning more about this.
Yeah, thanks, Abhi. Are there any questions?
Hello, sir.
Yeah. Oh.
List of variables, I think more than in Excel sheet, more than 1,000 are there, sir. So
yeah.
How to separate atmospheric models and oceanic models also? Here monthly data is there, daily data. In the list of there is no daily data, only monthly data and oceanic variable monthly data, atmospheric variable monthly data only is there, sir.
So yeah, so that's a good question. So I think the list that is in the table. So most of the models, as you know, are coupled models.
Yeah.
Unless those that are run the one that are run with only atmospheric model components with fixed SSTs, they are all outlined by the experiment IDs. So where is that? I think if you go to the CMIP control vocabularies, you have all these experiments that you can choose from. So, but if you want to know more details about like which variables correspond to either land or atmosphere sort of components, then I think what you need to do is just look at this table and look, try searching for keywords with ocean and atmosphere in it. So most of the variables are like we already know about. Let's say if you are working in a particular discipline, if you're more used to atmospheric variables, then you would probably know what variables you're after. Then what you can do is you can just try searching through this Airtable, or you can download it as a CSV, and then you can filter through it to see if that variable is available or not. So as I said, there's like no clear distinction whether it's totally relating to atmosphere or ocean. That would come from your own intuition, like which variable you're after. And using some keywords, searching through using keywords, you would find that some relevant variables would appear. But I don't know if there is any specific flag to separate atmospheric variables from oceanic variables, because these are mostly coupled models. So they would produce data set for the atmosphere and ocean in a single run.
Thank you, sir.
Other question? Yeah, Maxime has a question.
So in the table ID, some of these I don't know groups of data, some maybe data sets, they have something called extension at the end of it. What does that mean if it's an extension? For example, E1 hour is hourly atmospheric
Oh, okay.
extension.
I'm looking at the wrong one. Yeah. You mean this one? Oh, not this one. Here?
Yeah, a bit,
Is-
a bit. So maybe the page number 3 or so. Yeah.
This one.
Yes.
So I think what this would mean is that they would have like 3 hourly data sets, and then they would have a mean for the 3 hourly like a mean of all the hourly data sets embedded with it. So you have all the hourly data sets with 3 hourly means as well. So something along those lines, I think. So it has some extra variables which just relate to the means in different time horizons. So you would have, let's say you'll have 3 hourly data sets, and then you have 3 hourly means, and then you would also have a 6 hourly mean or something like that. So it's extended version of means in that data set.
Thanks. Any other questions? Yeah.
Hello. What are the fixed variables?
The fixed variables. So fixed variables are static variables. Let's say, for example, topography that's not changing in the model, or the land, sea, ice, mask. So those things that remain fixed. So you don't have to, it's not a function of time. So these are fixed in time. So static variables that are used in the model would be the fixed variables.
I think there is also a detailed documentation which describes all of these variables in some detail. So
yes.
you might want to actually read the detailed documentation. Each of these variables is kind of described in some detail.
Yeah. So you have Google Docs. Like if you click, yeah, you should see. So this is very similar to the Airtable, but if you go onto the CMIP 6 web page, you would get much more information on all these sort of variables. What would they mean? And these are all standardized. So all the groups around the world try to use similar sort of naming and conventions. So that's why they're all listed out there carefully.
Any other quick question, if there is any? Well, if not, let's thank Dr. Abhnil once again for staying back in the evening and telling us about CMIP 5 data and ways to access it, and also limitations. Yes, yeah. So I think, Abhi, thanks a lot. I
Yeah.
think